So what I want to do is to talk about the energy in an electromagnetic system. So you can visualize some region of space, some volume, which I will name V, and there are some charges inside, and maybe there are some circuits with some currents flowing, right? So we have a charge distribution, which can be a function of position and time, and we have a current distribution, volume current distribution J, which can also be a function of J and not J, of R and T, the position vector and time. Let me set up an axis system. So this is my position vector R, and wherever it points, there can be some volume charge and there can be some volume current. So you can imagine any kind of arbitrary distribution of these charges and currents. For example, I like to imagine some circuits, inductors, capacitors, and so on. And maybe there are some balls, solid spheres of some charge Q, right, making some electric field. Maybe there are some capacitors and so on, right? So the point is that there are electric fields in this whole system, and maybe some vectors are piercing out from the volume, right? These are electric fields, the white ones, and there are magnetic fields as well. Okay, let me use red color for magnetic fields and blue color for electric fields. I did not use blue, but anyway, there are some magnetic fields, and these electric and magnetic fields are connected to these charge distributions and current distributions by what are known as the Maxwell's equations. So the first law is that the divergence of the electric field is dependent on the volume charge distribution. So wherever there is some a bunch of charge clubbed together, the electric field will diverge away from that point. And similarly, the divergence of magnetic field is zero. So this just means that there are no magnetic monopoles. So B always curls around, and the field lines are circular, right? There is no origin of a magnetic field line and there is no sink for a magnetic field line. This just means that the divergence is zero, not that we know of, right? So there are no magnetic monopoles. The third tells us about the, not the third, the second, tells us about how E curls. So usually in electrostatics, the curl of the electric field is zero. That just means that if you move around in a closed loop, the total work done by the electrostatic field will be zero in electrostatic condition. But if there are changing magnetic fields, by changing I mean the magnetic fields that are changing with time. If these magnetic fields are changing with time, they will introduce a new kind of electric field, right? And we also call this an electric field because the force due to this field is also of the form Q times E. So this new kind of field has every right to be called an electric field, and the law is that the curl of that electric field is equal to the time rate change of this changing magnetic field. This magnetic field is changing with time, and by the way, these E and B, all of them are functions of position obviously and time as well. So it's a very general situations we are working with here. And the fourth law is about the curl of the magnetic field. So just like electric field, the magnetic field curls around a current, right? You must have done this problem in which you have a current and the magnetic field around this current is determined with this right hand thumb rule. So if you write down this in terms of volume current density J vector, by the way, if you don't know what volume current density is, the J vector is just the total current passing through some a little area. So if I draw this little area, call it dA perpendicular, right? So the current piercing through this area at an angle of 90 degree is called the volume current density. Obviously, as this dA goes to 0 and this di also goes to 0, but their limit, the limit of their fraction or this derivative tends to some finite value. So it is some finite sized vector, the J vector. So you can roughly think of J vector as a current. So wherever there is a current, the magnetic field lines like to curl around that current. So curl of V is directly related to this J vector. And there is another term, the famous correction, which is related to the changing electric fields, because there is just like how there is a changing magnetic field. By changing I mean changing in time. So correspondingly there is a factor which has this d e over dt in it, and there are some proportionality constants. So this factor has a whole story. So basically, if you want that the divergence of J is conserved, the charge is conserved, so you use this continuity equation. Divergence of J is d rho over dt, right? And if you apply this divergence in this fourth equation on both sides, uh, since the curl of the magnetic field is always zero, so this side is always zero. But if you did not know about this term, then the divergence of J would not be zero always. So to correct that, we introduce this one, and then you can use to find the divergence of this term. You can bring the divergence inside, because time and space are different here, and then you can use this divergence of E to replace this divergence with rho or epsilon naught to establish this identity. So this is nothing new. The content of this conservation law is embedded in these two equations. All right. So let me make some space. Okay, let me just erase everything so that we have some space over here. So this was like a quick recap of these four Maxwell equations. Now I want to talk about the energy. So the problem I am dealing with is the following: that if I have this charge distributed, this volume, right, V, okay, and this V might not be the whole space, maybe some subsection, and the surface is denoted by S. Okay, I'm writing V outside, I should write V inside, but and there are some charge distributions rho. You can imagine different charge distributions spreaded all around this volume, and there are some current distributions J, and due to these there are some electric fields, right, in this region. Some may be piercing out, and there are some magnetic fields as well, and these magnetic field lines and these electric field lines are connected to this rho or J by the four Maxwell equations, which I will just write down now. Divergence of E is rho over epsilon naught. Curl of E is negative d over dt of the magnetic field. Divergence of B is 0. And the last one, which is the longer one, is that curl of B is mu naught J. Again, remember that the J, if there is a J, the B vector will curl around that. And also if there is a changing electric field, there will be a magnetic field curling around that as well. So dE over dt. So these are the four Maxwell equations. Now let's say you want to know about the work done on the charges. So if there are these charge distributions spread all around this whatever, and these charges may be moving. These charge distributions can be moving in some direction. So you know that magnetic field acts on moving charges. Magnetic field, this if you have a moving charge, the magnetic field will act on it, and there will be a force which is given by this V cross B, and the force on the charge due to electric field is given by Q times E. So the total force law, Lorentz force law, is the charge, whatever the charge is, Q times electric field, and the part which is contributed from the magnetic field is V cross B. So if the charges are moving around, so there will be a magnetic force as well, and just by existing there, there will be an electric field on those charges. I want to know that in the next time interval dt, right? If I let my clock move on, and then I note what is the work done by all these electric and magnetic fields on all these charges in next 0.001 seconds. This is what I want to know. I have to calculate the quantity f dot dl, because this f dot dl is the work done on the charges. Now dl is the little displacement covered by this little section of charge. If I make some volume, this little volume, and I call this little volume d tau, and it is moving with some velocity v, right? This is my vector r vector which is pointing. There is some electric field at this point, the blue vector, and there is maybe some magnetic field as well. So I'll have to calculate q times that electric field, and I have to take the cross product of this v vector and that magnetic field vector at this point, and I have to multiply with the charge. The charge q is just the charge density rho at this point. This rho is a variable, a function of space and time, times the volume d tau. So this is the charge. And then I can calculate the force using this Lorentz force law, and I see what happens in the next time instant where this charge, this blob of volume maybe moves by this much. So this vector is dl. This is the dl vector, the little displacement it covered. And we have to do this for all these volumes. So basically I have to do a volume integral of calculating this f dot dl everywhere. So let me put in the expression for f. So f is q times E plus V cross B, where q is this rho d tau. So rho d tau, then E plus V cross B dotted with this dl vector. Now I can also write this dl vector as v dt, because this dl vector is displacement, and it can be written in terms of the velocity, because dl over dt is this velocity in this direction v. I will do that, dt times v. This is the work done in time dt on this little charge in this little volume d tau. I have to do the same thing for all these little d taus spreaded all around this volume. So I have to do the integral. It is a triple integral, but I'm writing this one, and this integral is done over this whole volume v. Then I can distribute this v inside. It is a dot product, and for this term v dot v, you see this term is like this, v cross b dotted with v. I can write the dot product over here, and then I can switch the places of cross and dot product, because the cross product follows what is called a Lie algebra. And so you can write this in terms of if you have a cross b cross c, you can write this in terms of not a cross b cross c, a dot b cross c. Then you can write this in terms of cyclic permutations. That is, you can cycle through this a, b, and c, and it will be the area, not the area, the volume, because this right here represents the volume of a parallelepiped formed by a, b, and c vector. And if you cycle through these dot products, it's like choosing a different base for your parallelepiped each time, choosing a different vector as your base, a different one as your height. It's just a matter of labeling things. So a dot b cross c, b dot c cross a, and similarly the third one, the c dot a cross b, all of them are equal in magnitude, as well as these are just equal vectors. these are same vectors. Not these are not vector. These are scalar quantities, and the value of scalar is same for all these three. Therefore, I can do this substitution. Anyway, technicalities aside, v cross v will be 0 because it's the same vector, and I will be left with this term when this v is dotted with this. I have rho d tau, I have v, I have dot e, and then finally dt integrated over this whole volume. I can put dt outside as well, and then I can club this rho and v vector as the j vector. So finally I can have my this is the work done by these electromagnetic fields in time dt. Therefore the work done per unit time is just the volume integral of E dot j over this whole volume. So let me write down the result at one corner. All right. So what we found is that the work done by electromagnetic fields per unit time dt is given by the volume integral E dot j over this whole volume. This just means that you go to a particular location, you find what the electric field is there, you find what the current volume current density is, you dot these two vectors and you get a scalar, and then you go to another volume d tau, then you do the same dot product, then you go to another volume and do the same for all this volume, integrate over this volume, and you can get your power. This is power at d w over dt. Now I want to focus on this term E dot j. What I want to do is to remove this j and write this j in terms of the electric and magnetic fields alone. So I can talk about the energy stored in fields. So I can use Maxwell's equations to do this substitution. I want j to be written in terms of these B and E. So from there you can see that j, from this last equation you can see that j is 1 over mu naught curl of B minus epsilon times partial E over partial T. So let me just write down E dot j for now. E dot j equals E dotted with curl of B, the whole thing divided by mu naught, minus epsilon naught times E dotted with partial E over partial T. If I talk about this term right here, you can see that if there was something like that, d over dt of some a dot b, two vectors, you distribute this derivative one by one, right? You use the product rule. You do a dotted with db over dt, and then you do b dotted with dA over dt. Now if the a and b are equal, let's say you substitute a equals b, so you have d over dt of a dot a, then this will be a, this will also be a, so that would just be 2 times a dot dA over dt, and this a dot a is just the square of the magnitude of this vector, so it is just d over dt of a square. Therefore you can write down this term as, if you bring the 2 over here, and similarly you have a similar term here, E dot dE over dt. So I can write down this term as half of epsilon naught, epsilon naught comes from here, and times dE over dt of E square. This is what I can do. And for the next term, which has these curl and E in it, let me just remove this. Okay, I will also remove this. I will paste this guy over here. Yeah. Now, similar idea for this term, right? You think of a derivative on E cross P, and you know that this is going to distribute over, right? on the divergence. So you know that this divergence will distribute over, and the identity is as follows. If you want to calculate the divergence of E cross B, I will put the proof in the description or any maybe somewhere else. But the identity goes like this. If you want to find a divergence of cross product of two vectors, what you do is take the second vector and take the dot product with the curl of the first vector, and then you do a similar thing. You take the first vector and take the dot product with the curl of the second vector. Okay, and there is a minus sign in between. So you can see that this E dot curl of B appears here. So I can rewrite this equation and rewrite this E dot curl of B as, so I have a 1 over mu naught, and then I have B dotted with curl of E minus not E curl B. This whole thing is multiplied with 1 over mu naught. Then I have half epsilon naught partial by partial t of E square. So this is the next step of simplification. Now what can we do next? Now I use again the content of the Maxwell equations to remove these curls of E and B. See, I can use this equation to remove the curl of E with this, and I can use well, let's leave this E cross B as it is. I have B dotted with curl of E, which is negative of partial B over partial T. Now again I have a similar term, B dot partial B over partial T, just like I had here. So again this B dot partial B over partial T can be written as half of partial B by partial T of B square, where B square is the magnitude of the square of the magnitude of the magnetic field vector. And there is a negative sign, so I have 1 over minus 1 over mu naught half of B square, a d over dt of B square. Then I have half, let me write this one down, epsilon naught d over dt of E square, and then I have negative 1 over mu naught, and I have this divergence of E cross B. So let me bring this 1 over mu naught inside. This is my final result. Let me just club some terms together. So I can club this half and minus outside, and also this partial derivative. So I have partial by partial t, right, minus partial by partial t of half of epsilon naught E square plus 1 over mu naught B square. Then I have minus divergence of 1 over mu naught E cross B. This is our simplified result for this E dot J vector in terms of electric and magnetic fields. And then when I take the volume integral, I have dw over dt equals to the volume integral of this whole thing. So let me take the volume integral, d over dt times the volume integral of half epsilon naught E square plus 1 over mu naught B square over d tau. And then I have the volume integral of a divergence, and I can use the Gauss divergence theorem to replace this volume integral with a surface integral. So whatever surface is enclosed, I mean whatever volume is enclosed by this surface, I can do the integral on this surface of this quantity. So I have a surface integral instead of 1 over mu naught E cross B. This is a vector quantity, remember, over this surface, where dA is this little patch of area dA. This is it. So now let's see what's going on in here. So if there are charges in the system, then the work done on them, the time rate change of the work, right? So in time dt, if you talk about it, the total amount of energy delivered to the system or the work done on these charges is equal to the d over dt of this thing right here. So, and since this is energy times the volume, so I can consider this part as the energy density of the fields. So if I again talk about this little section d top, the volume, there is some electric field, there is some magnetic field. If I take the magnitude square of E, take the magnitude square of P, sum them in this fashion, calculate half epsilon naught E square plus 1 over mu naught B square, then what I get is known as the volume density in the electromagnetic field. The energy, the volume energy density, whatever you want to call it. And this term right here is a surface integral of this vector. That means that you go to the surface, see what E is, see what B is, take their cross product, and then calculate this E cross B, and then you go to another surface and do the same for every surface and every little patch of area dA, and then add them up. You subtract this from this whole thing. So this means that if, let's say, you are doing some work on charges, or maybe there is some work done on the charges of this system in volume V, that must correspond to a decrease, because there is a negative sign, in this decrease of this quantity, which I'm calling the energy density or the energy stored in the magnetic field. This whole volume integral is the energy, and this integrand is the energy density, because this is a volume. D tau is volume. This means that if electromagnetic fields are doing some work, there is some work done on the charges. So maybe that work will increase their velocity or maybe their potential energy, whatever. That is the mechanical energy that is hidden in here. The idea is that if there is some work, that must mean if that work is done by the electromagnetic fields, so the energy density or the energy of the electromagnetic fields must go in to doing that work. That is, the energy density in the energy in the electromagnetic field decreases for the cost of that work. And there is another term which physically signifies the flow of energy that is piercing through the surface of this boundary. So you calculate E cross B, you take its surface integral, and then you subtract that. That means that if you have, let's say, this, you had your particle and it gained some velocity V, let's say. So it gained some kinetic energy. There was some work done on it. So in this volume V, who did that work? So this equation is an energy equation. It's an equation about the conservation of energy. So if the energies of this particle is increased, that must mean that the corresponding energy of the electromagnetic fields must decrease by this amount, and there may be some flow of energy outside this surface as well, and that outward flow of energy is encapsulated in this term. So you calculate the flow of energy which is leaving the system by calculating this surface integral. The surface integral tells you about how much energy is leaving through the surface, and this tells you about how much energy is decreased with time of the magnetic fields, and that must correspond to the energy gained by this particle. Maybe it's a mechanical, in the form of mechanical energy, maybe potential or kinetic or whatever. So let me write down this result once again, and this time I will introduce a new vector for this 1 over mu naught E cross B term. our result is if there is a change in energy, or maybe I should talk about power, right? But power and energy are related by a factor of dt. I can use them interchangeably if I want. Negative d over dt of this energy stored in fields, right? The energy stored in fields. So I can call it energy stored in electromagnetic fields. E electromagnetic is the volume integral of the energy density of the electromagnetic fields, where U electromagnetic is given by half epsilon naught E square plus 1 over mu naught B square. So these are just new conventions or new symbols I've introduced, plus a surface term, surface integral of a vector S. I'm calling that vector S, where this S vector is 1 over mu naught E cross B. And this vector is called the Poynting vector. It signifies the transport of energy or power, right? And if you take the surface integral of the Poynting vector, what you get is how much energy left the system. There was a negative sign here. Right. So if I want to write this in better notation, what I can do is bring this guy over to this side. This is the electromagnetic energy, and this must correspond to some mechanical energy. And then I have d over dt of this mechanical plus electromagnetic, let me call it a total energy. That would be equals to negative of s dot dA. Or if I turn it back into a volume integral, I can write divergence of s d tau, right? And I can, instead of energy, I can write this in terms of energy densities. So there is a volume integral, and inside that volume integral, I have energy densities. So, and this d by dt I pulled inside the volume integral, d by dt of total energy density, where this total energy density has the mechanical energy density plus this electromagnetic energy density, which is given by this. So, in a sense, you can write a differential equation which says that the time rate change of the total energy density is related to the divergence of the Poynting vector. So if you talk about this little blob of volume, and you see that the S vector, this E cross B vector, is diverging away from this little blob of volume, that must correspond to a decrease in the total energy density in this volume, because there is a negative sign here. I can pull the negative sign here on this side. So it is similar to the, in structure, it is similar to the continuity equation for the conservation of charge, which says that d rho over dt is divergence of J. That is, if you have some little volume and there is some current flowing outwards, that must mean that the charge in this little volume must be depleting. And the vice versa is true as well. Similarly, this is the continuity equation for energy. So if you have Poynting vectors, or if you have this E cross B is diverging away from this little point, then the total density of the energy must be depleting in this little volume. Now that being said and done, let's take some example to make some more sense out of this. First thing to note is is that this E cross B, if either one of these is zero, if there is no magnetic field, let's say you are working in a purely electrostatic system, or maybe there is no electric field, you are working in a purely magnetostatic system, the S vector, which is defined as 1 over mu naught E cross B, is 0, because if either E is 0 or B is 0, then this whole thing is 0. So that means in that case there is no, in some way there is no energy transport. I like to think about S as the transport of power or transport of energy. Well, let's say you have a charge Q, and you have a current flowing in this direction I, right? So the electric field by this charge is of this form. It's radial, right? Like this, and so on. And there is a constant current in this wire. Now, obviously, you see that the electric field is like this, and the magnetic field will curl around this wire in this fashion. So let's say if you want to calculate E cross B at a certain point, for example here, you take this E, which is downwards a bit, and then you take, well, let's not do it over here, let's do it maybe somewhere around here. You have E, you have B, you can take their cross products, right? E cross B, you have something which is in this direction. You can think about it in 3 dimensions. The point is, E cross B is not zero in this system. That means that there is some transport of energy. Now, what is going on? What I think is that if you want to sustain a constant current in this wire, you what see if there is some charge, right, and you want to push this charge in this direction, and you want to push it with some constant velocity because this I is given by lambda v. So if you fix the charge density and the speed is constant, then the current will also be a constant. And if you want to maintain this constant current, you have to maybe do some work against this field, because if you are pushing in this direction, you are feeling an electric field in the opposite direction. Once you reach this point, you're feeling an electric field in the same direction. So if you leave the charge by itself, it will either decelerate or maybe accelerate depending on where it is. But if you want to maintain this constant smooth flow of current, you have to locally maybe give some energy or maybe take out some energy so that charge can move in a constant fashion. So this, I think, uh, this local, we provide or we take out some energy from this this location, and that corresponds to this E cross B, or the S vector, the Poynting vector. It tells us about how we can, what is the flow of energy locally everywhere. So what is the flow of energy here, there, whatever, whatever is its direction, you can work it out. And similarly, if you want to maybe set up another example where electric field is constant, it is quite complicated because electric field is radial. You can charge up a capacitor, right? You can do some plus, maybe plus here, minus here, and you can have your electric fields, constant electric fields E. And if you want to have a magnetic field as well, what you can do is maybe maybe you can have a surface current. You can have some surface current K, like this, in both these plates. So imagine some long plates, right? And surface current is moving like this. So the magnetic field in the region inside is given by the right hand thumb rule again, and it is outside like this, out of the paper. This is the magnetic field. And if I want to talk about electric field, it is given by sigma or epsilon naught, whatever the vector is, let's say z cap, above direction. And the magnetic field is given by mu naught times surface current K, and this is in the direction x cap. And if I want to find the Poynting vector, I can do that. It would be sigma or epsilon naught mu naught K, divide whole thing divided by mu naught, this one, and then there is a E cross B, so there is a z cross x cap, and that would give you y cap. So you can cancel out the mu naughts and you will have sigma k over epsilon naught in y cap. I'm interested in this direction. So y cap is like this. So according to this Poynting vector, the transport of energy is in this direction. So a net energy is being supplied or being taken away, whatever, in this y axis, y direction. How can you see that? So see, there are charges, right, spread it over all over this plate, plus sigma and minus sigma. to sustain this current, constant current of positive charges moving in this fashion, and on the bottom in this fashion, you have to fight these positive or negative static charges, right? These charges will repel or attract on depending where you are talking about, where on the plate. And to sustain this constant current, again, just like in that case, you will have to maybe pump some energy in or maybe take out some energy, and that local delivery of energy is incompensated in this s vector. So it tells you about where in which direction the energy must be moving away from the system, or in which direction the energy is transported. So actually Veritasium did a video in which he talked about what happens in a circuit if you have a battery and you have some charges moving around. So who carries the energy in this circuit? And he claims that electrons are not the carriers of the energy. The electromagnetic field is actually the carrier of the energy. Whatever the magnetic field is, right? Whatever the electric field is, we take their cross product and we get this Poynting vector. And this Poynting vector carries the energy along this circuit. And we just do the cross product of E cross B. So that's another insightful video. You can see that video. I will link that. And yeah, I think this is it. You can do some problems if you want to, but the key idea behind all this mathematics is the conservation law, right? Again, I want to emphasize that you want to think about this theorem in terms of the energy gained by charges, or maybe the potential energy or the kinetic energy gained by charges, and that comes at a cost of a decrease in the electromagnetic energy, which is given by epsilon naught E square plus 1 over mu naught B square. And if there is some flow of energy which is outside, if some energy is flowing outside the system, you have to decrease that amount by as well, and that amount you can calculate by this surface integral S dot dA over this surface. So the increase in the energy of the system is just the decrease in the electromagnetic energy. So d tau times UEM d over dt of this whole thing, and subtract off any energy which is being transported away from the system. This is the equation of energy. You can actually do the analysis for a wire. So if you have, let's say, a wire and there is an electric field in this direction, which is a constant, you have a big wire, right? And you talk about what the magnetic field is inside this wire. So you can calculate that magnetic field using Ampere circuital law. Inside the wire, there is some constant current I in this direction, and you can actually calculate E cross B, and then therefore you can calculate S, and then you can do the surface integral of this S over this whole volume to calculate what is the energy being transported, and you will find that you will rediscover the heating law, the Joule's heating law, whatever it is called. The power is IV, right? You will rediscover that. So you can do this problem if you want.